Our universe thrives on organized chaos. Picture a single star like our sun, a steady beacon in the void. Now multiply that by 13. A Tredecuple star system is a gravitational family of 13 suns, all dancing through space together in an intricate, mind-bending ballet. By the end of this journey, you will have explored 30 of the strangest discoveries scientists have made about these cosmic marvels. What forces keep 13 stars from tearing each other apart? Could planets possibly exist in such a turbulent neighborhood? The answers will challenge everything you think you know about stability in the cosmos. What does such an impossibly crowded sky make you wonder? Finding the first of anything is a monumental task in astronomy. The initial confirmed Tredecuple system did not reveal itself easily. Astronomers had to sift through mountains of data, looking for the subtle gravitational signatures of multiple stars orbiting a common center of mass. The primary method used was radial velocity measurement. This technique detects the tiny wobbles in a star's light, the red shifts and blue shifts caused by the gravitational tugs of its unseen companions. Imagine trying to hear a single instrument tuning in a symphony of 13 different orchestras playing at once. That was the level of precision required. As the data poured in, a pattern began to emerge that was far more complex than a simple binary or even a quintuple system. The wobbles had wobbles, suggesting not just a few, but a whole crowd of stellar bodies. Direct imaging from powerful telescopes provided the next crucial piece of the puzzle, visually resolving several of the brighter members of this stellar family. Yet even with this evidence, the initial reaction among the researchers was one of profound disbelief. The statistical probability of 13 stars forming and remaining bound together seemed impossibly low. The data was checked and rechecked, with scientists questioning their instruments and their models before they could finally accept the truth. They were not looking at a data glitch. They were looking at a cosmic family portrait, a gravitational dance of 13 suns that had been ongoing for millions of years. Such a crowded system should fly apart in a cosmic instant. Yet these 13 stars persist, bound by an invisible architecture of force. The secret to their survival is not a simple, orderly dance, but a carefully layered chaos. They are organized into hierarchical groups. Think of it as a family within a family. Within the larger system, you will find smaller, stable units. Two stars might be locked in a tight, fast orbit around each other, forming a binary pair. Another group of 3 stars could be performing their own intricate waltz. These smaller, stable clusters then orbit one another, and all of them together orbit the system's common center of gravity. It is a gravitational Russian nesting doll, where order exists at every scale to contain the chaos of the whole. This is where computer simulations become our window into their world. When astronomers model these systems, they feed in the known masses and velocities, then let the laws of physics play out over millions of virtual years. The initial results are almost always violent, with stars being flung out into the void. But when the model includes these specific hierarchical arrangements, something remarkable happens. The simulation stabilizes. The orbits, though immensely complex, find a rhythm. They enter into what are called orbital resonances. This is when the gravitational pull between stars synchronizes their paths. For example, one pair might complete 3 orbits in the same time a distant triplet completes 2. This resonance acts like a metronome for the system, preventing the gravitational tugs from ever falling into a destructive, chaotic rhythm. It is a delicate cosmic ballet where every dancer is constantly adjusting their step to avoid a collision, all guided by the silent, relentless music of gravity. How does such a fragile balance even begin? The rhythm of their dance creates a light show that defies all prediction. When astronomers first pointed their telescopes at a Tredecuple system, they expected to find patterns, the regular dips in brightness that come from stars eclipsing one another in predictable orbits. What they recorded instead was chaos. The system's light curve, the graph of its brightness over time, looked less like a clock and more like a frantic heartbeat. It was a jagged, spiking line that refused to settle into any recognizable rhythm. This is the third great discovery, the unpredictable light curve, a phenomenon that makes these systems impossible to classify with traditional astronomy. The causes are as varied as the stars themselves. One moment, a hot, massive star passes in front of a cooler, dimmer companion, causing a deep, sharp dip in light. But before that dip can even finish, another, fainter eclipse from a different pair of stars begins somewhere else in the system, creating a complex, overlapping pattern of shadows. Meanwhile, individual stars are prone to their own violent outbursts. A colossal flare on one star, a sudden eruption of magnetic energy, can send the light curve soaring upwards in a matter of minutes, only for it to crash back down as the flare subsides. Then there is the light itself, bouncing between the 13 stellar surfaces. The intense glow from the hottest star can reflect off the atmospheres of its closest neighbors, adding a faint, shimmering echo to the overall brightness, a ghostly signature of their crowded proximity. Decoding this requires more than just observation. It demands sophisticated computer models that can simulate the gravitational dance of every single star and calculate the precise moment one passes in front of another, all while accounting for stellar activity and reflected light. It is like trying to reconstruct a symphony by listening to the overlapping echoes in a hall of mirrors. Each flash and flicker holds a clue, a piece of the puzzle in understanding the most crowded stellar neighborhood in the known universe. The most chaotic light show in the galaxy raises an even more profound question. Could planets actually form and survive within this stellar riot? The discovery of exoplanets in Tredecuple systems defies every conventional model of planet formation. In a place where gravitational tides constantly shift, the serene process of dust grains clumping together to form worlds seems impossible, yet against all odds, planets are there. Their existence suggests that the early disks of gas and dust around young stars can be far more resilient than we ever thought, managing to coalesce into planets even as 13 suns pull them in different directions. The concept of a habitable zone in such a system is almost comical. Around a single star, this zone is a placid, well-defined region where liquid water could exist. Here it is a flickering, unstable ring of possibility. A planet might bask in the warmth of one star, only to have its orbit carry it into the intense glare of a second, or the frigid darkness on the far side of a third. Its surface conditions would swing violently between scorching heat and deep freeze, a cycle of celestial seasons that would make life as we know it incredibly difficult to imagine. This gravitational turmoil creates a cosmic shooting gallery. A planet on a slightly unstable path is constantly at risk of a close encounter with a passing star. When this happens, the planet is not gently nudged. It is often slingshotted with immense force, ejected from the system entirely to become a rogue planet, drifting forever in the cold, starless space between galaxies. But some planets find a path through the chaos. They avoid the dangerous inner regions and instead settle into a grand, sweeping orbit around the entire central cluster of stars. Astronomers call this a P-type orbit. Picture a single world on a vast, lonely circuit, tracing a wide ellipse around the entire glowing family of 13 suns. From the surface of that world, the sky would be an unimaginable spectacle. Multiple suns of different colors and sizes would rise and set in complex, unpredictable patterns, casting multiple shifting shadows and creating a daylight that never truly ends. The very existence of these planets forces us to reconsider the definition of stability, suggesting that even in the most crowded corners of the universe, worlds can find a way. This stellar menagerie contains stars that should not exist in the same era. A single Tredecuple system acts as a cosmic museum, showcasing every stage of stellar evolution simultaneously. You might find a brilliant Blue-O-type star, a behemoth burning its hydrogen fuel with such ferocity that it will live for only a few million years. Right beside it, a tiny, cool red dwarf smolders quietly, destined to shine for trillions of years, outliving every other star in the system by 1,000-fold. This is not just a collection of different stars, it is a collection of different timescales, a living timeline where stellar birth and death happen in the same gravitational neighborhood. The presence of stellar remnants like white dwarfs and neutron stars adds another layer of profound strangeness. A white dwarf is the exposed, super-hot core of a dead sun, a dense Earth-sized ember that was once a star like our own. A neutron star is the collapsed, unimaginably dense core of a star that went supernova, a teaspoon of its material weighing as much as a mountain. Finding these stellar corpses dancing alongside vibrant, youthful stars presents a cosmic detective story. How did the supernova that created that neutron star not tear the entire system apart? The answer likely lies in the system's hierarchical structure. The violent death may have occurred in a tight inner binary, where the explosion violently altered the orbit, but was not powerful enough to overcome the gravitational glue of the wider system. This means that from the perspective of a planet orbiting the outer stars, the sky might have once hosted a temporary second sun, a supernova blast so bright it would have been visible in broad daylight, all while the other 12 stars continued their silent, untroubled dance. This extreme variety forces us to abandon the idea of a star system as a single, coherent family born together. It is more like a celestial metropolis, a gravitational city that has gathered stars of all ages and backgrounds, holding them in a delicate billion-year truce. The existence of this celestial metropolis presents the ultimate formation mystery. How can 13 separate stars be born together in one place? Our standard model of star formation involves a single collapsing cloud of gas and dust fragmenting into a few new suns, perhaps 2, 3, or 4. But 13 is a number that pushes physics to its breaking point. The leading theory suggests it all began with a single, monstrously massive molecular cloud core, a nebular womb of unimaginable density. As this core collapsed under its own weight, it did not fragment neatly. Instead, it shattered, breaking apart into a cascade of smaller clumps, each destined to become a star. This chaotic birthing process could have naturally produced the hierarchical groups we see today, with tight binaries and triplets forming from localized pockets of instability within the greater chaos. Yet even this dramatic scenario has its limits. Could one cloud really fragment into 13 stable pieces without the entire system flying apart immediately? Many simulations say no. This failure points to a second, even more dynamic possibility: stellar capture. Imagine this system starting as a smaller family of just 4 or 5 stars, born together in a dense stellar nursery. As they drifted, their collective gravity acted like a net, snagging other young, wandering stars that passed too close. In the crowded environment of a newborn star cluster, such gravitational theft could have happened again and again, slowly building the system up to its current improbable number. The truth might be a violent combination of both, a rapid initial fragmentation followed by a slower period of captures, a two-stage process that created a gravitational dynasty. Current models struggle because the initial conditions required are so exceptionally rare, a perfect storm of mass, density, and turbulence that may only occur once in a galaxy. This leaves us with a humbling thought. We are not just looking at a strange star system, we are likely looking at the sole survivor of a far more chaotic and violent era, a relic from a time when the galaxy was a much more crowded and dangerous place. The serene silence of space is an illusion, especially around a family of 13 stars. Amidst the visual chaos of eclipses and flares, astronomers detected something even stranger: complex radio whispers that pulse and fade without any discernible pattern. These are not the steady hum of a typical star. They are sharp, intermittent bursts of radio waves, crackling through the void like static from a broken transmitter. Decoding this signal became the next great puzzle. The first and most likely culprit is the immense magnetic violence inherent in such a crowded system. When stars with powerful magnetic fields orbit extremely close to one another, their magnetic lines can snap and reconnect, releasing colossal bursts of energy that we detect as a sharp spike in radio waves. It is a celestial short circuit on an unimaginable scale. Another natural explanation involves stellar winds. Every star emits a constant stream of charged particles, a wind that flows out into space. In a Tredecuple system, these winds do not drift peacefully away, they collide. Picture the solar wind from our sun as a gentle breeze. Now imagine 13 different hurricanes slamming into each other at millions of kilometers per hour. These collisions compress and heat the particle streams to incredible temperatures, making them glow brightly in the radio spectrum, creating a fluctuating, unpredictable radio beacon. Yet the sheer complexity of some recorded bursts forces scientists to methodically rule out every possible natural cause. This rigorous process of elimination is what gives rise to the most speculative and thrilling possibility. Could some fraction of these signals be artificial in origin? The idea is not that astronomers immediately cry alien, but that they must, by the rules of science, consider all potential sources, no matter how remote. This careful dance between skepticism and open-minded wonder is what makes the search so compelling. It transforms a simple radio signal into a cosmic question, a brief flickering moment where we must ask if we are listening to the weather of 13 stars or something else entirely. These radio whispers are born from a storm of unimaginable violence. Within the crowded orbits of a Tredecuple system, the stars themselves breathe out hurricanes of destruction. Every single sun is constantly blowing a stream of charged particles into space, a stellar wind that flows outward at supersonic speeds. Around our solitary sun, this wind is a steady, manageable breeze. But here, with 13 stars in close quarters, these are not breezes. There are 13 different hypercanes slamming into each other. When these immense outflows collide, they do not simply merge. They create titanic shock fronts, invisible walls of force in space where the material is compressed and heated in an instant to temperatures of millions of degrees. This superheated plasma then glows with the energy of a miniature sun, but its light is not the kind we can see. It screams its existence in the high-energy language of X-rays. Satellites designed to see this harsh light reveal the system not as a collection of peaceful points, but as a roiling cauldron of energy, flickering with intense, localized X-ray emissions that map the chaotic intersections of these stellar hurricanes. The consequences for anything caught in the crossfire are apocalyptic. A planet orbiting within this maelstrom would have its atmosphere systematically sandblasted away. The relentless pressure of these particle winds would strike like a cosmic fire hose, stripping away the protective layers of gas and hurling them into the void, leaving behind a barren, scorched rock. But the true scale of this violence is even grander. In the tightest binary pairs within the system, where two stars orbit extremely close, the powerful wind from a larger, hotter star can actually blow directly onto the surface of its smaller companion. Over millions of years, this can strip away the outer layers of the victim star, fundamentally altering its evolution and leaving behind a stripped-down, bizarre stellar remnant. This means the system is not just a place where stars live together, it is a battlefield where they actively reshape and destroy each other, a continuous supersonic conflict written in X-rays and stellar theft. The battlefield of colliding winds is just one symptom of a deeper gravitational war. These 13 stars are so close that their very shapes are under constant attack. The immense gravitational tides in the system literally stretch the stars, pulling them out of their natural, perfect spheres and into egg-shaped ovals. This is not a subtle effect. If you could stand on a hypothetical planet, you might see one of the suns appear distinctly elongated, bulging out toward its nearby companions as if struggling to escape its own skin. This distortion does far more than just alter a star's appearance. It reaches deep into its heart, disrupting the delicate balance of its internal nuclear fusion processes. In a stable spherical star like our Sun, gravity pulling inward is perfectly balanced by the pressure from fusion pushing outward. But when a star is stretched into an oval, this equilibrium shatters. The regions of the star pulled outward by tidal forces become cooler and less dense, while the compressed regions grow hotter and denser. This creates chaotic, lopsided fusion reactions within the core. The star does not burn its fuel evenly. It stutters and surges like a car engine, misfiring under a heavy load. This internal turmoil can have dramatic consequences. It can force the star to burn through its hydrogen fuel far faster than it should, shortening its lifespan from billions of years to perhaps only millions. More immediately, the build-up pressure from this distorted fusion can violently release through the star's surface. We are not talking about ordinary solar flares. These are titanic stellar eruptions, cataclysmic events that tear entire sections of the star's atmosphere loose and hurl them into space. The surface of such a star will be a perpetual maelstrom of activity, with magnetic loops the size of solar systems and spots of intense heat and cold driven by the relentless gravitational kneading from its many neighbors. This means the stars themselves are living in a state of perpetual, painful stress, their fundamental life processes twisted and accelerated by the simple, inescapable fact that they are never, ever alone. The relentless gravitational tides within a Tredecuple system do not just distort stars, they can also fling them away forever. Astronomers have tracked runaway stars, solitary suns hurtling through the galaxy at millions of kilometers per hour, and traced their paths backward to a shocking conclusion. Many of these stellar fugitives began their lives within impossibly crowded families like a Tredecuple system. This is the slingshot effect on a cosmic scale. The mechanism is a gravitational dance gone wrong. When three or more stars interact in a close pass, their orbital energy gets redistributed in a chaotic exchange. In most cases, the system finds a new stable balance, but sometimes the mathematics of motion demand a sacrifice. One star absorbs a tremendous amount of kinetic energy from the others, like a ball being struck by two swinging hammers at once. This energy boost is so powerful it exceeds the system's escape velocity. In a flash, that star is no longer a member of the family. It is a projectile, ejected from its birthplace and set on a one-way trip into the galactic void. These are not gentle expulsions. The star is launched at a hypervelocity, so fast it can cross the entire galaxy. Finding these runaways and plotting their trajectories is like cosmic forensics. By measuring a star's speed and direction with extreme precision, astronomers can rewind its motion across millions of years. When the backward trail leads directly into the heart of a known Tredecuple system, it provides undeniable evidence of a past gravitational catastrophe. Each runaway star is a ghost from the system's history, a permanent record of a moment when the delicate dance faltered and a member was violently cast out. This forces a startling revision of our understanding. A system with 13 stars today may have once contained 14 or 15, or even more. Its current state of precarious balance is not a pristine condition. It is the aftermath of a war, a quieter era that followed a period of even greater chaos and stellar ejection. The violence of colliding stars leaves behind a cosmic crime scene, scattered with the evidence of shattered worlds. When astronomers turned their infrared telescopes toward these systems, they did not just see the glow of the stars themselves. They detected a faint warm halo of dust, a sprawling debris disk that should have been cleared away by the stellar winds long ago. This was not a single, orderly ring like the one in our own solar system. Instead, they found multiple disks, each one orbiting a different subgroup of stars within the larger family, and each one tilted at a different angle. It is as if several separate solar systems, each with its own belt of asteroids and comets, have been thrown together into a single, chaotic gravitational blender. These disks are not made of fine dust alone. They are the sites of relentless, high-speed collisions. Within them, countless planetesimals, the building blocks of planets, are constantly smashing into each other. Some of these impacts are destructive, grinding fledgling worlds back down into rubble and glittering dust. Others are constructive, where smaller pieces manage to stick together, attempting to build new planets against impossible odds. This creates a glowing, infrared bright environment of perpetual chaos, a visible record of planetary construction and destruction happening simultaneously. The misalignment of the disks is the key to understanding the violence. It means that the gravitational pull of the various stars is constantly tugging these belts of material, stirring them up and preventing them from settling into a calm, flat plane. This stirring action ensures that collisions are not rare events, but a constant, frenetic drumbeat. The infrared glow we see is the thermal energy released from these endless crashes, a silent testimony to a battlefield where worlds are both born and annihilated in the same instant. The chaos of colliding winds and distorted stars is amplified by a force you cannot see. Deep within the tightest binary pairs of the system, astronomers found something even more fundamentally connected, the invisible threads of their magnetic fields becoming tangled together. These are not separate auras of power. They are fused into a single colossal magnetic structure that spans the space between the two stars. Picture two immense bar magnets, each the size of a sun, with their fields so intertwined they become one chaotic, knotted web of energy. This magnetic entanglement stores a staggering amount of power, a reservoir of stress that builds with every orbit. The release is not gentle. When the stress becomes too great, the magnetic field lines snap and violently reconnect. This event is a stellar short circuit of almost unimaginable scale. It unleashes a flare that dwarfs anything our sun can produce. A solar flare from our sun is a spectacular event. but a flare from one of these magnetically linked binaries is orders of magnitude more powerful. It is the difference between a firecracker and a thermonuclear bomb. For a brief, terrifying moment, the flare can outshine the combined light of both stars, emitting a lethal wave of radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. But the violence does not stop there. The magnetic reconnection often blasts a colossal cloud of superheated plasma directly into space, a coronal mass ejection of epic proportions. Where a similar event from our sun might take days to reach Earth, these ejections travel at a significant fraction of the speed of light. This creates a persistent and inescapably dangerous radiation environment throughout the inner regions of the system. Any hypothetical planet forming there will be subjected to a constant sterilizing barrage, its surface scoured by these recurring blasts. This invisible magnetic partnership proves that the stars in a Tredecuple system are not just neighbors. They are prisoners in a cage of their own mutual making, bound by forces that can both sustain their dance and threaten to tear them apart from within. The silent, elegant dance of these 13 stars hides a dark and violent history written in their very light. When astronomers analyze the spectrum of light from these suns, breaking it down into its constituent colors like a cosmic rainbow, they are reading a chemical story. On the surfaces of some stars, they find an anomaly, an overabundance of heavy elements like iron, nickel, and even gold. These are elements that a star of that type and age should have already sunk down into its core, drawn by its immense gravity. Their persistent presence on the surface is a telltale clue, the evidence of a stellar crime scene. It is the signature of cosmic cannibalism. The star has not produced these elements itself. It has consumed them. One scenario is planetary ingestion. A star in a close gravitational encounter with another had its orbit perturbed just enough to swing it through a region rich with planets or the debris of shattered worlds. As it passed, its immense gravity would have torn those planets apart, pulling their material into a glowing, temporary ring before devouring it all, enriching its outer layers with the digested remains of entire worlds. But there is an even more dramatic possibility. The chemical fingerprint on one star might indicate it consumed not a planet, but a piece of its own stellar sibling. In the tightest binary pairs, if one star expanded as it aged, its outer layers could have spilled over onto its companion. The larger star would have donated a portion of its own atmosphere, which the smaller, denser star then greedily accreted, forever marking its surface with the elemental signature of its digested twin. This forensic astronomy reveals that the current, seemingly stable hierarchy is a temporary peace treaty. It is the aftermath of a violent billion-year restructuring, where the losers were utterly consumed and the winners carry the evidence of their feast like a permanent stain. Amidst the gravitational storm, a strange kind of order emerges. Deep within the system's chaotic heart, astronomers found a pair of stars locked in a perfect, frantic dance. These two suns orbit each other so closely that their year is shorter than a week on Earth, whipping around a common center in a blur of motion. This is not a chaotic wobble. It is a metronome of incredible precision, a natural cosmic clock ticking away within the maelstrom. The discovery of this clockwork binary was a breakthrough for testing the very fabric of space-time. Einstein's theory of general relativity predicts that such massive, fast-moving objects will not orbit in a perfect static ellipse. Instead, their orbit itself should rotate, a slow pirouette of the entire elliptical path known as periastron advance. Around our sun, the effect on Mercury is tiny and takes centuries to measure, but here in this extreme environment, the effect is magnified a millionfold. The orbit of this tight binary pirouettes so rapidly that astronomers can observe the shift over just a few years. Each precise measurement of their orbital decay, the minuscule shortening of their period as they lose energy to gravitational waves, matches the predictions of relativity with stunning accuracy. It is a laboratory for fundamental physics on a stellar scale. The sheer violence of their surroundings makes this precision even more astounding. You would expect the gravitational jostling from 11 other stars to throw this delicate clock completely out of sync. Yet the inner binary persists in its perfect rhythm, seemingly immune to the chaos outside. This paradox reveals a deeper truth about the system's hierarchy. The same gravitational forces that create turmoil on a large scale can also create a protective bubble of stability for the innermost pairs, shielding them just enough for their exquisite dance to continue. a tiny, perfect gear in a machine of glorious chaos. The system's census of 13 stars was never the full story. The gravitational map revealed faint, ghostly neighbors on the outermost edges. Astronomers detected these new members not by their light, but by the subtle, persistent tugs they exerted on the inner family of suns. The entire central cluster would exhibit a slight, rhythmic drift, a gentle wobble that could only be explained by the presence of massive, unseen bodies orbiting far beyond the light. These are not bright, vibrant stars. They are failed stars known as brown dwarfs or exceptionally faint, low-mass red dwarfs, objects so dim they are virtually invisible against the blackness of space. Their orbits are almost inconceivably vast, taking not years or centuries, but many thousands of years to complete a single loop around the central chaos. Their discovery forces a complete reevaluation of the system's true size and population. The 13 brilliant suns we can see might just be the inner council, the bright, noisy city center. Meanwhile, these faint, wide-orbit companions are the distant, dark suburbs, silently tracing their immense, patient paths in the cosmic hinterlands. This suggests the system's gravitational influence extends far beyond what any telescope can directly see, a sprawling empire of darkness ruled by a glittering, chaotic capital. How many more of these faint ghosts might be lingering in the periphery, their presence still hidden from our most sensitive instruments? The light from these 13 suns tells a story of frantic motion, but to read it you have to break it apart. Astronomers use a tool called a spectrograph to split the starlight into a full rainbow, revealing a barcode of dark lines. Each line is a chemical fingerprint, an element in a star's atmosphere that has absorbed a specific color of light. In a calm single star, these lines are steady, but here they are a chaotic, shimmering mess. The lines do not hold their position. They shift wildly toward the blue end of the spectrum and then race back toward the red, over and over in a frantic dance. This is the Doppler effect in action, the same phenomenon that makes a siren's pitch change as it races past you. When a star moves toward us, its light is compressed, shifting the lines to blue. When it speeds away, the light is stretched, shifting the lines to red. With 13 stars all in motion, you are not seeing one set of lines wobbling. You are seeing 13 different sets of spectral lines, all shifting at different rates and in different directions, constantly overlapping and crossing over each other. The result is not a clean barcode, it is a spectral soup, an indecipherable tangle of shifting colors that seems to defy any attempt at understanding. Untangling this soup is a computational nightmare. It requires algorithms to hunt for repeating patterns, to identify the unique wobble of a tight binary pair amidst the slower, grander wobble of that pair orbiting a central triplet. Each successfully identified set of lines is like isolating a single voice in a choir of 13, all singing different songs at the same time. Yet, this confusing data is also an unparalleled treasure trove. From the speed and span of these shifts, astronomers can calculate the minimum mass of each star. From the period of the wobbles, they can deduce the precise timing of the orbits. This spectral chaos is, in fact, the most precise map we have of the entire system's gravitational dance, a direct recording of its relentless, multi-layered motion, written in light itself. This spectral map of motion reveals a gravitational puzzle that even Einstein's equations struggle to fully explain. The intricate dance of 13 stars possesses a stability that seems to demand more mass than our telescopes can find. All the visible matter, the glowing suns and the faint dust, does not account for the precise, cohesive rhythm of their orbits. This discrepancy has led to one of the most controversial hypotheses in modern astrophysics, the possibility that a hidden, invisible force is at work. The missing gravitational glue could be a localized, dense clump of dark matter. Picture this not as a diffuse halo, but as a tight, concentrated knot of the universe's most mysterious substance, nestled within the star system itself. Its gravitational pull would act as an unseen anchor, subtly reinforcing the system's structure and preventing it from flying apart over cosmic time. For this idea to be true, dark matter would need to interact with itself in ways we have never observed, clumping into these planet-scale masses that can directly influence stellar dynamics. The implications are staggering. Proving this theory would do more than just solve the mystery of one star system. It would revolutionize our entire understanding of dark matter, transforming it from a vague, cosmic-scale phenomenon into something that can leave a distinct fingerprint on individual stellar families. It would mean that the strangest star systems in the galaxy are not just celestial curiosities, they are potential laboratories holding the key to unlocking the nature of the universe's dominant, yet invisible component. The gravitational ballet of 13 suns might be choreographed by a ghost. This cosmic crime scene is also a factory for creation. Amidst the stellar cannibals and distorted suns, astronomers have identified a different kind of resident, a star in its final, glorious act of self-sacrifice. This is an asymptotic giant branch star, a bloated, aging giant nearing the end of its life. Inside its deeply layered heart, a frantic production line is running. Through a process called the slow neutron capture, or the S process, atomic nuclei are steadily bombarded with neutrons. One by one, these neutrons stick to the nuclei, building them up atom by atom into heavier and heavier elements. In this stellar forge, common elements are transformed into rare and precious ones. Carbon, oxygen, and even iron are the base materials. The end products are the stuff of jewelry and industry, elements like strontium, zirconium, and lead. The star becomes a cosmic alchemist, turning simple matter into complex riches, but the star does not hold onto this treasure. It is a factory with no warehouse. The immense energy produced in its core pushes outward with such force that the star's outer layers are blasted away in a powerful, persistent stellar wind. This wind is not like the gentle breeze from our sun. It is a gale of enriched material, a continuous eruption that carries the newly forged heavy elements away from the star's core and out into the surrounding system. This stellar wind acts like a cosmic farmer sowing seeds. The heavy elements are scattered into the vast clouds of gas and dust that still linger between the stars. They mix with this primordial material, enriching it with the building blocks of complexity. This enriched cloud is the raw material for the next generation. When gravity once again triggers the collapse of a gas cloud within the system, the new stars that form will be born with a higher metallicity, a richer inheritance of heavy elements from their stellar ancestors. Even more astonishingly, the planets that might coalesce from the surrounding disk of debris around these new stars will form from this pre-enriched material. The rocky cores of those worlds, their mineral compositions, and the very chemistry of any potential atmospheres would be seeded with the gifts from a star that died long before they were born. In a place defined by gravitational chaos, this is a cycle of cosmic death and rebirth, where the end of one star provides the essential ingredients for the beginnings of new worlds. This cycle of cosmic creation demands a sacrifice, and sometimes that sacrifice is a star that refuses to die. Deep within the stellar crowd, a white dwarf, the Earth-sized cinder of a dead sun, might be orbiting perilously close to a living giant. The immense gravity of the dense white dwarf begins to act like a vampire, relentlessly pulling hydrogen, rich gas, from the atmosphere of its bloated companion. This stolen material does not simply vanish, it flows onto the white dwarf's scorching hot surface, accumulating in a layer that grows denser and hotter with each passing year. For decades, even centuries, this process can seem deceptively quiet, but it is a quiet that is building toward an inferno. When the accumulated layer of hydrogen reaches a critical threshold of pressure and temperature, a cataclysm is unleashed. The entire blanket of stolen gas ignites in a runaway thermonuclear explosion. This is not a supernova that destroys the star. It is a nova, a colossal surface blast that can suddenly increase the star's brightness 10,000-fold. For a few glorious days, this reborn star outshines every other sun in the system, a brilliant temporary phoenix. Then the fury subsides, the expended hydrogen is blasted away into space, and the white dwarf returns to its dormant state, a cold ember once more. But the cycle does not end there. The companion star continues to bleed its atmosphere, and the flow of fresh fuel resumes. The white dwarf begins its feast again, setting the stage for another rebirth. This is the zombie star scenario, a macabre dance where a stellar corpse is repeatedly reanimated by consuming its partner. From the perspective of a distant observer, the system would flicker with these unpredictable, brilliant flashes, a cosmic lighthouse with a chaotic and violent rhythm. The sheer number of stellar interactions in a Tredecuple system makes this cyclical death and rebirth more likely than anywhere else, a perpetual resurrection written in fire and stolen breath. That chaotic static is more than just background noise. It is a permanent, inescapable feature of the sky for any world inside a Tredecuple system. Imagine a civilization rising on a planet orbiting one of these 13 suns. Their first tentative steps into radio astronomy will be met with a wall of sound, the constant crackle of magnetic reconnection, the shifting hiss of colliding stellar winds, and the sharp pops of stellar flares would create a radio cacophony, drowning out any faint, structured signal. Distinguishing an artificial transmission from a natural stellar outburst would be a monumental task, like trying to hear a whisper in the front row of a heavy metal concert. This endless interference would force any developing society to overcome a fundamental barrier. Their entire search for cosmic companionship would be skewed. While we on Earth listen for quiet, orderly signals, a civilization here would have to look for something else entirely. They might develop technologies designed to cut through the noise, perhaps using laser-based optical communication that can pierce the radio fog, or modulating their signals in a pattern that mimics the chaotic stellar flares themselves, hiding their messages in plain sight. The very nature of their attempts to communicate will be shaped by the need to be louder and more clever than the stars they live with. Their greatest technological achievements might be born not from a desire for quiet conversation, but from the sheer necessity of screaming to be heard over the deafening roar of their own suns. The eventual fate of the system's tightest binary pairs is written not in light, but in the fabric of space-time itself. These incredibly close stellar duos, whipping around each other in a frantic blur, are slowly but surely losing energy. The energy they shed does not vanish. It radiates outward as gravitational waves, faint ripples in the cosmic pond that stretch and compress everything in their path. For now, these ripples are too quiet for our current observatories to detect, but the future holds an extraordinary opportunity. Next-generation gravitational wave detectors like the Laser Interferometer Space Antenna, or LISA, are being designed to listen to the low-frequency hum of the universe. The mergers within a Tredecuple system will be a prime target. When one of these close binaries finally spirals in for its ultimate embrace, the event will not be a silent one. It will create a crescendo of gravitational waves, a specific chirp that rises in frequency and amplitude before cutting off abruptly at the moment of collision. This signal will be fundamentally different from the mergers we have detected from isolated black hole pairs. The presence of 11 other stars will leave a distinct imprint on the gravitational waveform. Their collective gravity will subtly tug on the merging pair, introducing tiny wobbles and frequency modulations into the signal. It will be like listening to a duet while hearing the faint, harmonious background of an entire choir. Decoding this complex signal will allow scientists to precisely map the gravitational environment of the entire system at the moment of merger, confirming the number and mass of the other stars in a way that light alone never could. This will be more than just observing a stellar death. It will be a final, direct measurement of the system's intricate architecture, a cosmic autopsy performed by reading the ripples it creates in reality itself. The gravitational architecture of this 13-star family holds configurations once thought to be purely theoretical. Astronomers mapping the orbits of one particular triplet found a stunning arrangement, a stellar-scale version of a Trojan configuration. Here, a smaller, dimmer star was not orbiting its larger partner. Instead, both were orbiting their common center of mass, but the smaller star was perfectly trapped 60 degrees ahead in the same orbital path, locked into a stable gravitational pocket known as a Lagrange point. This is a point where the gravitational pulls of the two main bodies and the centrifugal force of orbit perfectly balance, creating a kind of celestial parking spot. We have long observed this with planets like the Trojan asteroids that share Jupiter's orbit around the Sun, but to find a full-size star, an object of immense mass and gravity itself, acting as a Trojan companion to another star, was a profound shock. It meant that these stable points, these gravitational eddies, were robust enough to anchor an entire sun against the chaotic tides of the surrounding system. The discovery redefines our understanding of orbital stability in extreme environments. This is not a fragile, temporary alignment. For the smaller star to remain in this Trojan position, the masses and distances involved must be exquisitely precise. Its continued presence proves that even amidst the gravitational noise of 11 other stars, these pockets of perfect balance can persist for millions of years. It is a testament to the system's hidden order, a demonstration that within the apparent chaos, the fundamental laws of physics still carve out havens of predictable, clockwork motion. What other celestial surprises are hiding within these gravitational sanctuaries? This unexplained warmth is a ghost in the machine, a heat signature without a clear source. Even after accounting for every star and every known debris disk, a persistent infrared glow remains. It is a thermal whisper that should not be there, a blanket of warmth spread across the system that our models cannot explain. This anomalous infrared glow points to energy being released from something we cannot directly see, a hidden component of the system radiating in the silent language of heat. One compelling theory points to dust, but not in any ordinary location. We are not talking about rings of debris orbiting single stars. This glow could be coming from a vast, diffuse cloud of fine, warm dust that permeates the entire inner system, a cosmic fog. For this dust to remain warm, it must be continuously heated. The most likely source is the intense starlight from the 13 suns, but there is a problem. The radiation pressure and stellar winds from so many stars should have blown this fine dust away entirely, clearing it out in a relatively short cosmic time. Its continued presence means something must be constantly replenishing it. This suggests an environment of relentless grinding, where small asteroids and comets are pulverized in collisions so frequent they create a permanent, shimmering haze of fresh dust, a cloud that is constantly being destroyed and recreated. Another, more speculative idea involves the system's faint, distant companions. Could there be a population of rogue planets, worlds ejected from the inner system and now drifting in the darkness, that are generating this heat? These would not be placid, cold worlds like Pluto. Their surfaces could be kept warm by intense tidal forces. If their orbits are highly elliptical, the gravitational pull from the central stars would constantly flex and knead their interiors, generating massive internal friction through tidal heating. This process could give them warm, geologically active surfaces, perhaps with volcanoes spewing lava into the perpetual night, their collective infrared output adding up to the mysterious glow. The most exotic possibility, however, ventures beyond conventional physics. Could we be seeing the thermal signature of something entirely new? While highly speculative, some have pondered whether certain theoretical particles or interactions could manifest as a faint, distributed energy source. Ruling out every known astrophysical object is the first and most difficult step, a process that turns this unexplained warmth into one of the system's most tantalizing mysteries. It is a reminder that for all we have learned, a Tredecuple system may still be hiding its most profound secret, not in the brilliant light of its suns, but in the faint, warm darkness between them. That faint rising hum is the sound of a stellar countdown. Deep within the system's core, the innermost binary pair is locked in a final, intimate dance. As they whirl around each other, these two massive stars are not moving through empty space, but through the fabric of space-time itself. Their immense acceleration creates ripples, gravitational waves that carry energy away from the system. This slow, steady energy drain has a profound consequence. The stars are losing orbital altitude, spiraling inward toward each other in an ever-tightening embrace. This is not a slow geological process. On a cosmic timescale, it is happening in a flash. The entire merger could occur within just a few million years, a blink of an eye for the universe. As the stars draw closer, their orbital frequency increases. They whip around each other faster and faster. The gravitational waves they emit rise in both pitch and amplitude, creating a specific signal known as the chirp. It is a cosmic siren song that starts as a low thrum and escalates into a high-frequency shriek just before the final collision. This chirp is the direct, audible proof of Einstein's general relativity in its most extreme environment. For astronomers, detecting this signal from a Tredecuple system would be the ultimate prize. It would not just confirm the fate of one binary pair. The precise shape of the chirp, its timing and modulation, would be exquisitely sensitive to the gravitational influence of the other 11 stars. Their collective tugs would leave tiny fingerprints on the waveform, allowing scientists to map the entire system's mass distribution with unprecedented accuracy. We would be witnessing not just a stellar death, but the revelation of an entire gravitational architecture through the final, frantic song of its innermost stars. The light from these 13 suns carries hidden messages in its very polarization. When astronomers analyze not just the color and intensity of the starlight, but the specific direction its waves are vibrating, they unlock a new dimension of understanding. This technique, called polarimetry, acts like a pair of cosmic 3D glasses, revealing structures within the system that are completely invisible through traditional observation. The principle is one of scattering. As light from a star travels outward, it encounters countless tiny dust particles floating in the space between the suns. When light bounces off one of these minute specks, its vibration direction is often shifted or polarized in a way that depends on the angle of the collision. By meticulously measuring the polarization pattern from the entire system, scientists can work backward. They can trace the path of each polarized photon to deduce the precise location, density, and orientation of the dust cloud that scattered it. It is a form of celestial cartography using light itself as the pen. The resulting map is never simple. It does not show a single neat disk. Instead, it reveals a chaotic, three-dimensional labyrinth of dust lanes and gas filaments. You can see the dense, swirling disks that still cling to individual stars, the raw material for future planets, but you can also see vast, ethereal bridges of dust stretching between these stars, temporary structures twisted into spirals and loops by the relentless gravitational tides. These are not static sculptures, they are dynamic rivers of material, flowing and reshaping in real time as the stars dance through their orbits. This polarized light shows us the system's anatomy in a way ordinary light cannot, exposing the intricate skeleton of dust upon which the entire stellar family is built. These stars hold a chemical secret in their light, a fingerprint that defies the galaxy's own history. When astronomers measured the system's metallicity, the total abundance of all elements heavier than helium, they expected a familiar number. Our Sun, for instance, is a fairly metal-rich star, a product of billions of years of galactic enrichment from countless stellar deaths, but this family of 13 broke the mold. Its overall metallicity was not average. It was an extreme outlier, either shockingly high or perplexingly low. A high metallicity suggests a privileged birth. This system would have formed from a cloud already seeded with the ashes of many prior supernovae, a cosmic inheritance of heavy elements that implies it was born in a bustling, productive region of the galaxy, a stellar metropolis. A low metallicity, however, tells the opposite story. It points to a primitive origin, a birth from pristine, almost pure hydrogen and helium gas that had been scarcely touched by previous generations of stars. This would make the system a relic, a living fossil from the galaxy's early, more barren youth. Both possibilities are problematic. A high metallicity system of 13 stars is incredibly rare, as such enriched environments are usually too turbulent to allow for the calm collapse of such a large, cohesive family. A low metallicity system is even more puzzling, because the early universe lacked the heavy elements that act as cooling agents, making it notoriously difficult for giant clouds to fragment into so many individual stars. This metallicity puzzle forces a radical conclusion. This Tredecuple system did not form through the galaxy's standard gradual process. It is an immigrant, a celestial oddity with a unique origin story. Perhaps it was born in a dwarf galaxy that was later cannibalized by our own Milky Way, a surviving fragment of that ancient collision. Or maybe it formed in an isolated, dense pocket of the galactic halo, a region so quiet and undisturbed that it preserved a unique chemical signature lost to time. The very elements that make up these stars are not just fuel, they are a cosmic passport, stamping this stellar family as a stranger in a familiar land. The data stream from these crowded systems occasionally spikes with a flash of impossible light. Astronomers have cataloged brief, ultra-bright flares that outshine even the most violent magnetic reconnection events, flashes so intense and anomalous they resist all easy classification. These are not the predictable eruptions of a stressed star. They appear at random, blaze with the ferocity of a small supernova for a few hours, and then vanish without a trace, leaving only a mystery in their wake. The debate over their origin is fierce, with several competing theories vying for acceptance. One possibility involves a cosmic illusion known as microlensing. If an invisible, dense object like a rogue planet or a primordial black hole were to drift perfectly between us and one of the system stars, its gravity would act as a lens, bending and magnifying the star's light for a short period. This could create a sudden, dramatic brightening that mimics a flare, a ghostly fingerprint from an object we can never see directly. Another, more extreme theory posits an unprecedented scale of magnetic activity. Perhaps in the tightest stellar binaries, magnetic fields can become so convoluted that their reconnection is not a simple snap, but a chain reaction, a domino effect of energy release that culminates in a single titanic flash far beyond anything our models predict. Yet the most intriguing flares are those that fit neither profile. Their light curves and energy signatures are alien, matching no known natural process. Could we be witnessing the explosive demise of a planet being torn apart by tidal forces, or the collision of two gas giants? Or does the answer lie in something entirely new, a stellar phenomenon that only emerges in the crucible of a 13-star gravitational pressure cooker? Each of these phantom flares is a cosmic question mark, a brief, brilliant challenge to our understanding of what stars are capable of. The stars themselves are travelers on a galactic highway, and their motion holds the secret to their origin. By charting the precise, minuscule drift of the Tredecuple system across the sky over many years, the Gaia satellite has done more than just map its current path. It has provided a cosmic time machine. The data reveals that all 13 stars share an identical, peculiar velocity, a specific speed and direction that sets them apart from the general flow of the Milky Way's rotation. This shared motion is a ghostly fingerprint, a relic of a shared birthplace. When astronomers reverse engineer this trajectory, tracing it backward across billions of years, the path did not lead to a random point in empty space. It converged directly upon the location of a long-vanished open cluster. These clusters are the galaxy's stellar nurseries, dense families of thousands of stars, all born from the same giant cloud. Most of them disperse over time, their stars scattering into the galactic disk like dandelion seeds in the wind. The fact that this Tredecuple system stayed together while its siblings drifted apart is a testament to its incredible gravitational cohesion. It is the one tight-knit family that refused to break up after leaving home. This kinematic link is a profound discovery. It allows scientists to pin down the system's age with unprecedented confidence, dating it to the same era as the parent cluster's formation. More importantly, it reveals the violent nursery that forged it. To survive the chaotic gravitational environment of a young, dense cluster, the system must have formed quickly and with an exceptionally stable hierarchical structure from the very beginning. It was not a gentle birth, it was a trial by fire, a brutal selection process where only the most gravitationally robust families could endure the close encounters with other stellar groups and emerge intact. This system is not just a random collection of stars, it is a living fossil, a preserved relic from a specific moment in our galaxy's history, carrying the unique velocity of its ancestral home like a permanent stamp on its passport through the cosmos. 13 stars may be the edge of cosmic possibility. This final discovery is not about what we have found, but about what might be fundamentally impossible. Astrophysicists are locked in a fierce debate over whether a Tredecuple system represents a natural upper limit for gravitational stability. Is 13 the absolute ceiling for how many stars can be bound in a single, coherent family? The mathematics of orbital dynamics suggests there is a breaking point. With each new star added to the system, the number of gravitational interactions does not increase linearly. It explodes exponentially. The delicate network of hierarchical orbits and protective resonances that keeps a 13-star system intact becomes impossibly fragile. Introducing a 14th star would be like adding another wildly spinning top to a table already crowded with them. The chances of it finding a stable, long-term orbit without triggering a chain reaction of ejections are vanishingly small. Computer models consistently show that systems with more than 13 stars tend to be violently unstable on short cosmic timescales, rapidly shedding members until they settle down to a smaller, more manageable number. Yet the universe has a habit of defying our neat predictions. Could even more extreme systems be hiding in the galactic shadows? The challenge is one of detection. A system with 15 or 20 stars would be so gravitationally chaotic that its light curve would be a permanent, indecipherable jumble. Its stars might be so faint and crowded together that our telescopes see them only as a single, blurry smudge of light. Their orbital periods could span such vast timescales that we have simply not observed them long enough to see the full pattern of their dance. The debate, therefore, remains open. Is the Tredecuple system we have studied the ultimate example of stellar togetherness, a natural limit imposed by the laws of physics? Or is it merely the most complex system we have been clever enough to identify so far, a signpost pointing toward even more crowded and bewildering families of suns waiting to be found? The answer will ultimately define our understanding of how far nature can push the boundaries of chaos and order. The hunt for more of these 13-star families is a race against data. Our galaxy is a haystack of 100 billion stars, and finding a single, impossibly rare Tredecuple system within it seems like a task for centuries. Yet the search is accelerating, driven by a combination of cutting-edge technology and the collective power of human curiosity. Massive surveys from telescopes like TESS and Kepler have provided the raw material, a flood of light curves from millions of stars. Each curve is a story, a graph of brightness over time that holds the secret to what is orbiting that distant sun. For a single star with a planet, the story is simple, a single repeating dip. For a Tredecuple system, the story is a chaotic, spiking novel. The challenge is that no two of these novels are exactly alike. Their gravitational dances are all unique, producing light curves of bewildering complexity that do not fit any predefined template. This is where machine learning enters the stage. Scientists are training sophisticated algorithms not to look for a specific pattern, but to recognize the hallmarks of pure chaos. They feed the computers known examples of complex systems and tell them to find more data that behaves in similarly unpredictable, multi-layered ways. The algorithms act as digital bloodhounds, sifting through petabytes of information to flag the most promising, most bizarre candidates for human astronomers to investigate further. This partnership is uncovering stellar arrangements we never thought to look for, revealing that the architecture of star systems is far more creative and diverse than our textbooks ever allowed. But the machines are not working alone. Citizen science projects have opened this cosmic treasure hunt to everyone. Platforms like Zooniverse allow anyone with an internet connection to look at real light curves and help classify them. The human brain is still exceptionally good at recognizing patterns that machines might miss, the subtle intuition that something just looks strange. Thousands of volunteers are now scanning these graphs, and every so often, someone spots a flicker that is just a little too frantic, a little too messy to be a simple binary. That one click can put a previously ignored star on the map for professional follow-up, turning an amateur astronomer into a co-discoverer of one of the galaxy's most extreme gravitational families. The early results from this global effort are already hinting at a staggering possibility. These 13-star systems might not be the solitary freaks we once believed. They could be members of a larger hidden population, a class of ultra-complex systems that has simply evaded our notice until now. If that is true, then our map of the cosmos is about to be redrawn, revealing a universe that is far more crowded, far more chaotic, and infinitely more wonderful than we ever dreamed. We have traveled through 30 layers of cosmic wonder, from the first detection of a 13-star family to the final, haunting possibility that we have witnessed a natural limit to stellar togetherness. These systems are not merely astronomical curiosities. They are extreme laboratories where the fundamental forces of the universe are stretched to their breaking point. Gravity reveals itself not as a simple tether, but as a master choreographer of chaotic hierarchical ballets. Stellar evolution unfolds not in isolation, but in a violent shared timeline where stars consume each other and die in spectacular, repeating cycles. The very concepts of stability and habitability are rewritten in the flickering light of 13 suns. Each discovery peels back a layer, showing us that our conventional models are but a quiet prologue to the galaxy's true, riotous story. The cosmos is far stranger, more dynamic, and more creatively violent than we ever supposed, so we turn this final question to you. Of these 30 revelations, which one reshaped your view of the universe most profoundly? Was it the stellar zombies, the gravitational crime scenes, or the faint radio whispers that could be anything? Let us know in the comments below, and if your curiosity for cosmic mysteries is not yet satisfied, subscribe to continue this journey with us into the deepest wonders of